So, have you guys taken the organic chemistry lab yet? Great, so you remember the section of the lab where you do your reaction and then you need to purify it. So you put it into a separatory funnel, add another liquid, close it, shake and vent, then you get two distinct layers and you drain out one of them, keep the other. Well, that's what we're looking at today. That's the principle of liquid equilibrium. So what we're working towards ultimately are these ternary diagrams, which allows us to view the composition at different points. But first I want to go over some of the key terms that we'll be using. So we're going to be using A, D, and S typically, where A is our solute and also our target material. D is the diluent, which is the solution that our target material is stuck in. And then S is the solvent that we're going to use to get it out. And what's going on is that we have a case where A is soluble or miscible in both of these liquids, but those liquids aren't soluble in each other. That's why whenever you can add them together and shake it up, the solvent that you add will actually steal the A away from the diluent, and you just keep doing that until you can get all of your product out. And so whenever you mix it together, of course, you get the light layer, which is usually called the extract. We mark that with E a lot. And the heavy layer, which is called the raffinate, we mark that with R. So looking at ternary diagrams, they'll usually appear in two forms. These actually look better. There's rectangular, which appears as the right triangle. This is the one we're going to be focusing on the most and actually using. And then there's the triangular one, which this one is not going to be used so much in this class, but you'll see it in a lot of other classes. They'll use the same structure where if you have three materials, they'll usually correspond to a point. I prefer whenever it's written like this because it makes it easy to read. So to talk a little bit about the triangular coordinate system, the way that you would read this is at each point is a pure substance, A, S, and D. This curve right here represents the two-phase region where within the concentration points within this curve are where you'll have that light layer and that heavy layer. Above that is a single phase region where everything will actually mix together and stay as one liquid that you can't separate. So the way you typically read points on this is, say if I wanted to point right here, you could view these points as, with this being 100%, the base of the triangle corresponding to each point would be 0%. So you could read the lines going up. So, can you see my mouse cursor from there? Shows up. So you just do one point at a time. So if we wanted to start with A, that disappears right here. You can either okay, I didn't know it did that. You can count down from either 100 or count up from 0. So if I have it right here, 200, 90, 80, 70, 60, 50, 40. And you do that for each point to get your final value for the actual concentration. And we're going to cover this a lot more with these rectangular coordinates. Next lecture is going to be all just finding values for the concentration. I just wanted to give a brief overview today. So here it's kind of the same thing, except now we have D, which is always going to be our X, and A, which is always going to be our Y. In these cases where the points are 100%, and this line actually represents the solvent line. So you can read it the same way, where if you wanted to know a concentration, you would just pick a coordinate point, read the x value, read the y value. So the question becomes, how do you get the solvents percentage? And what you do for that is just the math balance. The total composition has to equal 1 or 100%. So it's just a matter of subtracting your A and D from 100, and you get that. And if you wanted to actually visually represent it for lines, what you could actually do is just take each point on the X and draw a line connecting it to the Y, and those would be your solvent lines that you could count like before. So far, so good? And please stop me if I'm moving too fast or if you have any questions. So with that, I'd like to move to how these are actually made. So this is an example that we're going to look at that it's from the Learn Chemie YouTube channel, where we have this data set here that represents equilibrium concentrations in a weight percent of 2 layers. So we have acetic acid as a solute, A, which is our target. We have water, the diluent that we're trying to remove it from, and we have isopropyl ether, which is the solvent that we're going to use to remove it. And what they did is they took a bunch of concentrations together, did the shaping and venting, and then measured the compositions of both layers and put them here. And so we have the water layer and the isopropyl ether layer. So we'd start out, and I'm going to kind of cheat because a lot of this is pre-made. We'd start out by putting our diluent in the x-axis, our target or solute in the y-axis, and we can draw our solvent line by just connecting the points. This is the point of 0 solvent. And that's how we get our triangle. So the next thing that we would need to do is make our equilibrium curves. And the way that we do that is simply just by plotting these points. We would plot the water layer, and then we plot the isopropyl ether layer. So for example, whenever I add the water layer, it appears here, and the isopropyl ether layer is going to make up the other portion. And there's kind of a gap here. Something that I didn't mention before are pi lines, which are related to the equilibrium. What they actually are points that, or lines that connect the points of the equilibrium. So the way these would be made is just, for example, right here is the, so it'd be connecting these corresponding values. So for example, if I wanted to make one pi line for here with these first values, it would just be a matter of making a line between the 2 points. That one's hard to see. So if I wanted to make one connecting these last values, which is going to be this one at the top, which will actually finish off our curve. And that's what we get. So far, so good. And so skipping ahead to the end result is whenever we can get all of our tie lines together, we can use these to find different points of equilibrium. But what these points are mainly important for is the conjugate curve, which the conjugate curve is made just by plotting the x values from our water in the water layer, or our D in the D layer, and then our A in the S layer. Can double check that. Yeah. And so what this conjugate line is used for is that whenever you have these diagrams, a lot of the times you might not have these individual points. And so if we had a point where we'd want to find the equilibrium concentration, we would need to use that conjugate line. So going to be finding a good way to represent that. So for example, here I actually have a ternary diagram where we don't have those points. This is the full diagram. This is zoomed in because this is the part we care about. And once again, here in this top portion is the single phase region. That is where everything is one phase. We only have one composition to really worry about. Underneath this curve is where we have two distinct phases. That's where the two liquid layers separate out, and we can separate the phases individually, but also each one has their own respective composition that we'd ultimately have to find. And so if we don't have the points, but we want to make tie lines, what we would do is, for example,
Arsenal X.
sure. Pretty much, for example, if we had a point here and we wanted to make a tie line, it's just making a right triangle using this conjugate curve. Go straight down, then across. And so not only will we have our composition for the other layer, but we would make our timeline like that. And those are the lines that we see here. Where in the same case, all these lines really are. Does anyone have any questions about anything so far? Then in that case, I did that a lot faster than I thought. So we can actually start looking at how to read some of these points. And I can go over what's going to be expected for you in terms of homework and the exam. So for the homework and the exam, pretty much what you're going to be given is a diagram like this. And you're going to be asked to do a few things. First, you're going to be given various points on the diagram, say maybe one right here, maybe one here, and then another one maybe then. Actually, I don't like that one. Go with here. So you're going to be asked to find the compositions of these points And you might also be given something like markup points where we have your D, your A, your S, and maybe a point where we have, I don't know, say A is like 60%, D is like 25%, S is 5%. So what you'll need to do is identify these points and mark the points and give these some names. This will be W, Y, B. These will be K, K, L. So these points are pretty straightforward. So for pure D, that's just a matter of going to this tip of the triangle where D is 100%, and that would be our point J. For pure A, it's the same thing, although I can't do it on this one, but it'd be probably somewhere right there. And then pure S would be where we have 0 acetic acid, 0 water. So those would be those 3 points. And then next would be identifying the compositions at these points. So this point W is very easy and straightforward. It's just a matter of reading the graph. So we just look at it. Our D, that's going to be 10%. RA is at 45. And then we just do the math balance to get our S. So 100 minus 55 would be 45. So that's point W. Point W is very straightforward. And am I still good with everybody? All right. So then in that case, next we would look at points Y and Z, which are a little less straightforward. Y is more straightforward. Z can be kind of tricky. Space. So let's start with point Y. This is where we have a point that is lying exactly on this equilibrium curve. So what that means for Y is that we're going to have to use the tile lines. First, we can find the composition of this point. So check. Yep. So on this side of this curve is where it's going to be our extract, the E. On this side is where it's going to be our raffinate. And we can know that because whenever we were making it before, we know that these are 2 curves joined together. And probably around here is another tie line. So for Y, since we're on that E side of the curve, we can start out with finding our E composition, which to roughly eyeball this, I would say this looks like. B is about 8. So A is maybe about 24. So I apologize for being left-handed, so I cover everything that I write as I'm writing it. And then we would just do the mass balance to get the remaining, which would be 60. Said 68, 68. Thank you. I'm terrible when it comes to the math. But that's only one half of it, because since we're on this line, we're going to have 2 different layers. So now what we have to do is use a tie line. Shows a terrible point for the actually. So we take our point, go to that conjugate curve, and then go straight up from there. This would be our R for this case. This one being our E. We'll call that R1 and E1. And so now that we have that tie line, we need to find the composition at this point. And it's the exact same thing from this point on, where this be about, call that 56. Call that maybe 30, maybe 38. Someone help me with the math, so I'll stand here for an hour. 6. And so that's how we would find a point that's going to be on the curve. And I can guarantee you're gonna have a point that's in the single phase equilibrium, a point that's on the curve, and a point that's gonna be in the middle. The point that's in the middle is the one that's actually going to be a bit of a headache. And what I'll do for the next lecture is we'll do more of this. I'll actually print these out and give them to you so that you can follow along. So I'm gonna erase everything. Oh, my points. Z, I'll put it here. So whenever it's in the center, we don't really have a good way to make a tie line, which can be kind of a headache. Because what we're gonna have to do is a more iterative process, where we're going to have to make a guess at what the tie line might be, and then hope that we can get a right triangle that connects with the right angle base being on this line. If not, then we adjust our slope until we get it. So I'm just gonna make a guess going here. Then I'll draw my line straight down. No way I got that first one. So you see, I'm a little bit low. So I know that I need to bring this line higher. And I need to bring this line more to the side. That tells me that I'm gonna need to lower my slope a little bit. So try again a different color. So let's try this. And overshot it. And it can be a tedious process. Also, don't have a straight edge. Make sure that you have a straight edge whenever you're doing these usually. but you just keep adjusting, so.
So,
Yeah.
so basically, like, if you keep getting in like an obtuse triangle, you keep fixing it until you get that perfect right,
What
perfect
you,
90-degree, right? What you're trying.
you're gonna get a 90-degree triangle every single time, what you're trying to do is this base corner, you want to lie exactly on this conjugate, curve. Cause what you're trying to do is you're trying to actually identify the tie lines. You need to, cause those tie lines that go across are equilibrium points. So if you have a tie line that goes through the point, you can now split it into your two compositions. So whenever you make the tie line for this point, you'd be able to identify the composition of the extract and the composition of the rabbit. Does that make sense?
Yeah.
And once again, please stop me if I'm going too fast or something doesn't make sense. We're gonna be spending a lot of time next lecture on this as well. But let's try the black, you know, it's gonna be somewhere in the middle, so maybe about right here. That one is pretty close. So now that we have that, we can identify our points. And then it's just the same thing that we've been doing, where we now get composition of this point and this point. That makes sense? Any questions? I'm moving through this a lot faster than I thought I would. Yeah, so unfortunately, these markings aren't gonna show up in the Zoom call. So that's why next time I'm gonna make sure to print them out so that you can follow along. So one last check, do we have any questions? All right, we'll go ahead and end the Zoom call.